Hi, my name is Silent Dad. This video will contain solutions for the exercises in the C programming language book by Kernighan and Ritchie. Exercise 2-9. In a 2's complement number system, x and equals x minus 1 deletes the rightmost one bit in x. Explain why. Use this observation to write a faster version of bit count. So first, what is a 2's complement number system? So a 2's complement number system is a system in which numbers or integers are represented in its binary form. So for example in an 8-bit system, the 2's complement of the number 7 is 0000111. So another example is the 2's complement of the number -7, which is 1111001. So the 2's complement number system is just a representation of the decimal numbers. So the decimal numbers or integers, signed or unsigned. Okay, so the exercise requires us to explain why this expression deletes the why this expression deletes the rightmost one bit. Okay, the best way is to get the best way is to get a certain number x and find its 2's complement representation, and also the 2's complement representation of that number less than 1. So let's look at a certain table. So from the computer science handbook, there is a table that represents there is a table of binary representation of numbers. So in this table we have the sign magnitude representation, 1's complement representation, and 2's complement representation. But we are only after the 2's complement representation. This is an example only for a 4-bit system. So let's take for example the number 7, the decimal number 7. The 2's complement representation is 0111. So let x equals to 7. So 2's complement representation of 7 is 0111. 0111. Okay. So if x is 7, therefore this is 7, So the if x7, the x minus 1 is 6. So the 2's complement representation of 6 is 0, 1, 1, 0. 0, 1, 1, 0. This is the 2's complement representation of 6. So performing an AND operation between the two will yield us this result 0, 1, 1, 0. This is the output, which is, so as you can see from this as you can see from this, the rightmost one bit of x, which is in this case 7, is masked to 0 when performed an operation between the two. So that is the reason. So the reason. So since it is masked to 0, it effectively deletes the rightmost one bit. So the rightmost one bit is masked to 0, thereby effectively deleting the rightmost one bit. Okay. So that is the reason why rightmost one bit is deleted. So based on this observation, we can create a faster version of bit count. So first let us see what is the original version of bit count. Bit count function. Original version. So bit count is this. So bit count sin x and b for b equals 0, x is not equal to 0, and x right shift 1 if x and 0, 1 increment b and then return b. Okay, this is the original version of bit count. So from the observation above, we can create the faster version of bit count by counting how many times the rightmost one bit is deleted. So int bit count. So we're going to use, so since the original version uses unsigned numbers, we're going to use as an argument also the unsigned numbers. So int b. So we're going to, since we're going to count the number of times the rightmost one bit is deleted, so for b is equal to 0, and we're going to stop counting when x is 0. So x is equal to x and equals x minus 1 and return b. Now how is this much faster than this compared to this original version? So by virtue of removing, by virtue of having this, our new bit count function having less instruction as compared to the original bit count function, so we can safely assume that it is faster than the original bit count version. So let's try to check if our function is correct. So let's put some comment here first. count 1 bits in X. So printf bit count, the number is, let's say, 15. So this should return as an output 4. Let's compile. Two dash 0. So let's try 16. Should output 1. Okay. So let's try this number. 8. So let's try 1, 2, 7. 7, of course. 1, 2, 8 should be 1. Okay. So since we get the result that we should be expecting, so we can safely assume that our bit count function, or we can safely assume that we have answered, fulfilled the requirements of this exercise. So that will be all for now, and I hope you learned something.